Our second exercise on Ansys Workbench will be this truss problem. Now, if you look at this problem, again it is subjected to a static load of 2500 newtons. That means again this will be a static structural analysis as far as our Ansys is concerned. So therefore, we will be again we'll have to make use of the static structural from this analysis system to carry out this analysis. So just drag the static structural and drop it here. We can rename this as 1D truss, and the same thing what I will do is I will also save this file with the name of 1D truss. You save it in a safe location, probably D drive 1D truss. All right. So the problem which is given here is we need to find, we have a truss which is made up of 4 members, and then we need to find what? We need to find the stresses in each element. We need to find the reaction forces, probably the reaction at these two ends which are fixed. Reaction here, there will be only vertical reaction here, because in the horizontal direction it is freely allowed to move, right? Since it is on roller support, there won't be reaction in the horizontal direction at this place, but there will be definitely one reaction in the vertical direction. And we need to find the nodal displacement. Probably we will look at the displacement in vertical and horizontal direction at this point and at this point. The properties like E of the material and area is given to us. So let us start. Our first step whenever we perform the analysis in Ansys is that first to select the type of analysis. We have already selected it, that is static structural. Then the second step is to give the engineering data to the software. We will have to input the engineering material data to the software. This we had seen in detail in our last exercise. So we won't be going by the default material which is already present, that is static structural, but what we will do is we will click here to add our new material. And since there is only one material here in all the parts, so we will create only one material. I will call it as material 1. You can name it anything, you can even name it as steel or something. Now this is an isotropic elastic material. We are doing the linear elastic analysis, so I will take this isotropic elasticity from here and I will drop it on material 1. It is asking us for these values of modulus of elasticity or Young's modulus and Poisson's ratio. Now in this case the modulus of elasticity is given as 210 GPa, which can be also written as 210 multiplied by 10 to the power 3 megapascals, or 210 multiplied by 10 to the power 9 pascals. Right. So we will enter the value as 210 multiplied by 10 to the power 9 pascals. 210. Now 10 to the power 9 we can very well type it as E9. So the software will take it as 210 multiplied by 10 to the power 9 pascals. Right. And then it is asking us about this Poisson's ratio. Now again this is a one dimensional analysis. We can give any value for Poisson's ratio, it will not make any difference. We will give it as 0.3. Okay, so we have defined our material. Once we define our material, we will close this, we will save it once. It is a good practice to save our data after finishing each and every step. Let us now go to the geometry. Now again, as we had seen last time, we can, if we have the geometry with us, ready-made geometry, we can import it, or else we will design it in the design modeler. If you are using the older version, you will not see this option, that is the space claim option, but you will see only this option, that is new geometry. Click on that. Once you click on that, the design modeler will open, wherein we will now model our truss. So this design modeler is opened now. In order to sketch, as we had seen last time, we'll have to choose one plane. Let us choose this XY plane. Right click on it and then say look at. So we have selected this XY plane. The controls remain same. I had explained in detail about this mouse controls for the software. Then we'll sketch on this XY plane now. In order to sketch, go to sketching and then go to line. If you cannot see these letters like P and C, you need to put on the constraints. For that, I had told you last time, go to the constraints and then go down and make sure that this option of auto constraint, under this auto constraint, this global and cursor is on. Okay, so go back to this draw option, click on line, and we have to draw now the sketch of the truss. Right now, if you look here carefully, this truss are in terms of meters. This is 4 meters, 3 meters, since this is 4 meters, this is 3 meters, also this will be 4 meter and this will be 3 4, then this should be around 5 meters, which it will take automatically. But what I'm trying to tell you earlier is, since the dimensions are already in meter, we need not convert this into mm. So we'll keep it as it is. We'll just zoom in a little bit. We'll just zoom in a little bit so that we get an idea of around 4 meters. So from here to here, it is approximately now 4 meters, right? So what I will do, I will start my sketch from here. From here, I will approximately stop here. Make sure that your line is not like this. You bring the line in such a way that you can see this edge. You can see this edge letter, right, which is telling us that our line is horizontal. So I have clicked this first line. Then what I will do, I will similarly now take this endpoint, I will go vertically upward, right, and then I will make sure that this V alphabet is visible, which tells us that our line is vertical. I will click here somewhere, and then similarly again click the endpoint of this line, and then make sure that H is visible, and then once you see this C, click on that. So we have created 1, 2, 3, 4, 1, 2, 3 members. Then one member is here in between from this point to this point. Now once our sketch is over, we'll go to dimensions. We'll click general, give the dimension to this member as how much? It is of 4 meter, right? So enter 4, and then again similarly give the dimensions to this vertical member, and then this should be, I think, 3 meters, right? Yeah, this is 4 and this is 3. So we'll click here. We will say that V2, right, this dimension V2 is of 3 meters. So that's it. We have done our sketch. Uh, the material and the cross section of this entire 4 members are same, right? So we did not take the option of the new sketch and all the way we had taken last time. Since here the material and the cross section is same for all the members, we can just finish our sketch on the sketch 1 itself. Once the sketching is done, go to modeling, and then remember we have to give the cross section to this. Now the cross section, what they have given is, the cross section they have given it as 0.1 meter square. So accordingly we will have to adjust our dimensions. So since this total area is 0.1 meter square, we can probably go for a rectangular cross section of dimension, let us say 0.2 multiplied by 0.5, right? We can do it this way, 0.2 multiplied by 0.5. So once I multiply this 0.5 by 0.2, I will get it as 0.1 meter square. So this is what we will choose now. Our cross section is rectangular cross section of 0.5 multiplied by 0.2. So in that case, I need to go to concepts, go to cross section, go to the rectangular cross section, and then give the dimensions to this as what? 0.5. This is B and this is H. Give H as 0.2, give B as 0.5. So this will give us the area as 0.1 meter square. You can see it here, right? Even you can see the moment of inertia about x-axis, product of inertia, moment of inertia about y-axis, and so on. All these things you can see. Okay, so we have constructed the cross section of 0.1 meter square. For that, after that, what we will do is, if you remember, we have not created any line bodies here. We have 0 parts and then we have 0 bodies. So before assigning this cross section, we need to create the line bodies, right? So for that, what you need to do is, you will have to go to this XY plane. You will have to go back to this sketch, and then, because as I had told you last time, ANSYS will not understand your sketches. It will only understand the bodies, like line bodies or the 2D plane bodies or the 3D three-dimensional bodies. So since this is a 1D sketch, I will have to convert them into 1D line bodies, right? I will have to convert them into line bodies. For that, go to concept and then click on lines from sketches, and then it is asking us the object which we need to convert. I will select on this, press Control, select on this, and then again holding this Control key, select on this and select on this. So I have selected all the line bodies. Click on Apply. Alright, once you click on Apply, then we have to generate now line bodies. So either you can right click on this and say generate, or you can even click directly on this icon here. I will click on this and then it will create a line body. Now what will be missing in this line body? Definitely the cross section will be missing. Although we have created, we have not assigned this cross section to this line body, right? So this cross section, that is rectangle 1, we have to assign to this line body. So therefore, since it is showing us this, asking us about the cross section, it is showing us it is not selected. Click on this not selected, you will get this drop down arrow. You click on that and then select rectangle 1. So that means now you have assigned the rectangle 1 to this line body. Alright, so we have completed our sketch. We will save it at this stage, and then it is a good habit of just minimizing it if you want, because I usually don't prefer to close this geometry unless and until I finish my analysis. So I have just minimized it so that whenever I want, I can just maximize it and change whatever changes I want to do. Okay, so after completing this geometry, again let us save this project, and then now the fourth step is to go into model. So I will click on model, I will right click on model, and then as we had seen last time about this setup, solution and results, we will take care inside this model itself. So right click on this model and then say edit, or you can even double click on this model. Now it will open the mechanical window, right? It is showing here starting mechanical. Depending upon your computer speed, it will take some time to open this. Now it has already opened. Yes, it has already opened. And by the way, if you had to really, if you wanted to check whether your cross section has been properly assigned or no, what you all could have done here in case of design modeler is you could have gone to view, and then you could have even clicked on the cross section solids, which will show you the cross sections which are properly assigned. All right, you may check it this way whether your cross sections has been assigned to this line body or no. Anyways, going back to this mechanical window, this has appeared here, right? This has appeared again. If you want to check whether this cross sections are properly assigned, you can go to view, and then you can click on this, you can click on cross section solids, right? You can see here properly that this cross section has been assigned to this line body. Now once this is done, we need to make sure that the material is properly assigned to this line body. For that, just click on line body, because by default Ansys will still take static structural as a default material for our line body. But what we have done, we have already defined a new material, right? So we'll have to assign it now. For that, just click on this static structural, you will get this arrow here, click on that, and then assign our new material, that is material 1. So now this line body has taken a proper material, that is material 1. Since we have finished assigning the material, the next step is we already know about this cross section. So the next step is to generate the mesh. Now for generating the mesh, we know that this is in terms of mm. This is as long as around 4,000 mm, right? So once I go into meshing, we can give some sizing to your elements. You can say, you can even mesh it first. Let us try to mesh it with the default size. Let us check what is the mesh size it is giving us. Say generate mesh. So it is giving us pretty well mesh. All right, if I just put off this cross sections, if I put off these thick shells and beams, it will show us this mesh. It has given us a very decent mesh. If you want to make it more fine, always what you can do is under sizing, you can go to this element size and you can change it to whatever size you want. We'll go ahead, we'll proceed with this element size itself. It will not make much difference here. All right. So after this, what we have to do is, once the meshing is done, the next step is to give the boundary conditions. Right now here again the boundary conditions will be essential boundary conditions and natural boundary conditions. So these are our essential boundary conditions. It is fixed at this node, it is fixed at this node, and also there is a displacement boundary condition at this node, right? It is on the roller support at this node. So these three are called as what? Essential boundary conditions. Essential boundary condition. And then the load which is applied here at this node, this is called as the natural boundary condition. All right, so we'll have to apply all these three: essential boundary conditions and natural boundary condition. Let me remind you, boundary conditions are very important. We need to make sure that these boundary conditions are properly assigned. So in order to do that, what we will do is, we'll click on static structural. The moment we click on static structural, we will see that this tab is opened here. Go to supports and go to fix support. Once you click on fix support, let me just put off this cross sections also. So once you click on fix support, we have to fix this node, right? But this node is we are unable to select this node. The reason is we are on face selection here. All right, similarly we can also select edge, but in this case we want this point, right? We want this node, so we'll have to select this vertex selection. Click on this vertex. Now we shall be able to select this point. Click on that. Once it is highlighted in green color, click on apply. So it is telling us that this has been fixed now. There is a fixed support here at this node. Similarly, again we'll have to go to the supports, fix support, and we'll have to also fix this point, right? So click on that and then say apply. Okay, so now if I click on again static structural, it is showing me that there is a fixed support at A, there is a fixed support at B. All right, you can even rename them, fixed support to something else, fixed support at A, fixed support at B. That way you have to just right click on this and then say rename, and then you can say fixed support at A or whatever. And then if just to avoid the confusion at the later stages, you can just rename it as fixed support at B. All right, so once this is done, then we have to give her a appropriate support at this point also, right? There is the support is not fixed there, but there is a roller support, right? So that means basically this point, this node is free to move in this direction, in x direction, but we are not allowing it to move in this vertical direction. Yes, so therefore we have to give a proper appropriate boundary condition there. Again, click on static structural, click on supports, and go to displacement. Once you go to displacement, you see here that you are free here to give the displacements in x direction, y direction, and z direction the way we want. So first of all, let us define this boundary condition at this node. Select here. Once it turns green, click on apply. Then it should be very free to move in x direction. So this x should remain free, but the displacement in y direction and z direction should be 0. So click on this free and make it 0. Similarly, then again click on this free and enter 0, and then enter, and then press enter. So this is the boundary conditions. These are the essential boundary condition, in fact, right? Fixed at A, fixed support at B, and then displacement at this node C. Now I will have to define the essential boundary conditions, that is the force at here, and then there is one more force here which I had missed earlier. See here, if you can see here, there is one more force at this node itself in this direction, right, of 2000 Newton. So we'll have to define both these forces, 2500 Newton and 2000 Newton. So how to define that? Again, click on the static structural. Now go to loads and then go to forces. Click on this node. Once it turns green, click on apply. Then what you do is you can either change this from vector to components, and then I want a force in negative y direction, right, downward direction of what is the magnitude. The magnitude is 2500 Newton. So what I will have to do, I will have to go to this y component, and then I will have to enter minus 2500. So it will take now the force of minus 2500 in downward direction, that is in the direction of negative y. Similarly, now I will have to apply one more force, that is again go to this, click on the static structural, go to this load, click on the force, then click on this node and then say apply, and then change this vector to component, and then click on this x component and then type 200, I mean 2000. All right, so there is a force of 200 Newton in the positive x direction. So now if you click again once again on the static structural, you will be able to see all the boundary conditions. These three are essential boundary conditions, these two are natural boundary conditions. Okay, so once these boundary conditions are given, then we are done. We have almost given everything which is required in order to carry out the solution of this problem. So at this stage, it is always a good practice to save our file. So we will save it once, and then once this is saved, we will right click on this solution and we'll ask the software to solve it. Right, it will take some time depending again upon your processor and RAM. It will take some time, and then ultimately it will solve this problem. Okay, so it has solved this problem. Once it has solved this problem, it is not showing us any solution as such, because we have not asked the software to give us any particular solution. In order to do that, right click on it, right click on this solution, go to insert, again go to beam tools, and then click on beam tool. All right, just expand this. You can check the direct stresses and all. Right click on this, again go to beam tool, go to deformation, and then ask for directional deformation, and then this will give you the deformation. Since we have asked for directional deformation, it will give you deformation in x direction, right? It will give you the deformation in x direction. Similarly, if you want to find the deformation in y direction, what you can do, you can again right click on this beam tool, and then go to insert, beam tool, deformation, again directional deformation. But this time what you do, change this x to y. So this will give you the direction in y direction. So let us rename this just to avoid confusion. This directional deformation, will rename it to in x direction. All right, and this directional deformation, we will rename it to directional deformation in y direction. Once this is done, we need to also find the forces in each member. For that, what we need to do is, we need to right click on the solution, go to insert, go to beam results, and then click on axial forces, because we know that there will be only axial forces in each members. This truss members can take only axial forces in its axial direction, right? So we can right click on this axial, we can right click on the solution and ask for the axial forces. Now after this, we also want to find the reactions at this different supports, right? So what we need to do is, again right click on the solution, click on insert, then click on probe, and then click on the force reaction. Now we want to find the force reaction at this A, right? At this fixed reaction A. This was our fixed support A. So click here. All right. So this will give us the force reaction at A. So just right click on this, rename it, and then just type it as at A. So this will give us the force reaction at A. Now similarly, again I want to find the force reaction. So what you can do is, you need not again right click on this and then say force reaction and all. Just right click on this force reaction, and then you can say duplicate without results, and then finally you will have to change this fixed support at A as fixed support as B. So it will give us the reaction at this point. Just right click on this and then rename it as B. All right, this will give us the the force reaction at B. Similarly, we want to find the force reaction here in the vertical direction also. So what we'll do, we'll say again right click, say insert, and then go to probe, click on force reaction, and then say displacement, click on this displacement, and then we are, I think, good to go. We have almost asked for everything that we want. Right click on it and then say evaluate all. Let me remind you, it will not solve this problem again. It has already solved. Now it has only, what it has done is, what software has done is, it has only evaluated these results. So now let us check these results one by one. Okay, so the axial forces, let us first check the axial forces. So axial forces looks to be same in all the member. It looks to be equal throughout its length in all the members, right? So here, if I just click on this view, and if I click on this thick shells and beams, if I go to the probe and if I just click here, it is showing us that here the forces are 431.2 in this member, Newton. But if I click here, it is showing us the forces as minus 504.33. And you must have guessed it right, it is showing us minus forces because here in this members the forces will be compressive. And same thing will happen here. Here also it should be minus, because here also in this member the forces will be compressive, right? But then again here it will be under tension, the forces will be under tension, so it is showing us as positive values. You must have you can check it from here, right? Since we are applying the force on this member will be under compression, even this member will be under compression, so therefore the forces are shown in this each member as minus, whereas this will be under tension, also this will be under tension. So it is showing us the forces as minus. So we have found what are the forces in each member. All right. We can also look at the direct stresses. Now, the direct stresses again, since the areas are same, since the cross section area is same throughout, the direct stresses also should be same. I mean, it should be constant over the length, and that should be equal to what? Let us check. It is equal to around this much. This value, that is 4.312 multiplied by 10 to the power minus 3 megapascals. Okay, in this it is showing it as minus, stresses as minus, because those are compressive stresses. Here there are what it is a tensile stress, and again here there will be compressive stress. Now you can see that there is some changes in stress which is observed here at these nodes. If I just put off this thick shells and beams, you can see that there are some changes in the stresses at this point. That is some error, and then if we just refine our mesh at that location, if we increase the number of nodes and elements in this area, we can overcome that error also. Okay, now let us look at the axial forces. If I just click on the axial force, we have already seen these axial forces. Let us look at the reactions. I mean to say, what are the reactions at this A? It is showing the reaction in this direction. It is telling us that the reaction is minus 431.2 in the direction of X. All right. So you can see here the reactions at X, I mean at point A in X direction, in Y direction, and so on. Similarly, at B, we can see the reaction here, the reaction in X direction, the reaction in Y direction, we can see here very clearly. Similarly, the reaction at the displacement, all right. The reaction at the displacement, that is at this node, the reaction is only there in the y direction, vertical direction, and as we had expected, the reaction in x direction is 0, because we had given a displacement in such a way that it can move freely in x direction. Therefore the reaction in x direction is 0. Reaction in z direction should be also, I think it should be 0, because there are no forces in z direction. This is a very small value, to the power 10 to the power minus 11 or something. So this is almost negligible. So it is 0. All right. So this is how we can solve any truss problem. You may verify this truss problem by either solving it by energy method, or you can go with your basic methods which you all must have studied in engineering mechanics and your MSOL, or you can solve it by energy methods, or you can even solve it by finite element method by doing hand calculations using this as the stiffness matrix and this as the equation of truss element. All right, so you can do that. You can verify whether whatever results they have obtained are correct or no.